A 3.9 kilogram mass, which I'll call mass 1, hangs from a string that is looped over a pulley projecting out from a tabletop. The other end of the string is attached to a 6.5 kilogram mass, mass 2, on the tabletop, such that between the pulley and mass 2, the string is horizontal. That's actually quite an important point. Assuming that both masses are already moving together, and that the coefficient of kinetic friction between mass 2 and the table is 0.21, find the acceleration of mass 1. So let's draw a free body diagram for mass number 1. There's the mass. We have a weight. Weight is of course equal to m times g. So 3.9 times 9.81, 38.26 newtons. Then we have a rope that is pulling upward with some tension. How about the other mass? It's a 6.5 kilogram mass. It has a tension pulling it to the right, which is the same tension that's kind of holding mass 1 up. What other forces do we have on this 6.5 kilogram mass? Well, we have a downward force that's equal to the weight, which is 6.5 times 9.81. But can you see that in this case, the normal force, which points up, and the weight will have the exact same magnitude, 6.5 times 9.81, 63.77. And then there's also a coefficient of kinetic friction. So friction force, which is going to go right here, is going to equal the coefficient of kinetic friction times the normal force. So I can calculate that right away to be 13.39 newtons. This is where we stand so far. I've just recopied those free body diagrams for you. Let's go ahead and write a Newton's second law equation for mass number 2. This mass number 2, is going to be sliding to the right. I hope you remember the picture from the previous slide. So I'm going to choose to the right to be positive. T minus 13.39 is equal to the mass of the object times the acceleration. We can't solve this equation because we have two unknowns in it. Now let's go to mass 1 and write a Newton's second law equation for mass number 1. Mass number 1 is moving downward. So I'm calling downward positive. 38.26 minus t is equal to the mass of the object, which is 3.9 kilograms, times the acceleration. That also has two unknowns. I now have a system of equations, two independently derived equations with two unknowns. I'm going to call the first one asterisk. I'll call the second one double asterisk. And here's what I'm going to do. I'm going to solve the first one for t. Add 13.39 to both sides. And then in double asterisk, I'm going to plug that in. So right here in double asterisk where it says t, instead of putting t there, I'm going to put 6.5a plus 13.39 in there. Just like that. Notice I've kept that negative sign right there. If we distribute the negative sign correctly, combine like terms, we're going to get this expression, and the acceleration is 2.4 meters per second squared. As we've discovered here, sometimes we run into cases where both our parallel and perpendicular F equals ma equations contain two unknowns, usually the same two unknowns. When that happens, tackle it just like you learned in your math classes. Solve one F equals ma equation for one variable, and then substitute that expression into the other F equals ma equation. That will give you a single equation with a single variable. Solve it, and then you can plug that solution back into either of your initial equations to find the other unknown.